In the previous examples, we had vector fields of length 2. This is a vector field with 3 components. Wanted to show you how to deal with the issues we're dealing with in that situation. So the first part says show that this is conservative. We know that this will be conservative if its curl is equal to 0. So let's find the curl of the function. It's going to be I hat, the partial with respect to x, and then y squared. J hat, partial with respect to y, and 2xy plus e to the 3z. And k hat, partial with respect to z, 3y e to the 3z. We got to get really efficient at computing curl. So for the I components, I have the y derivative of 3y e to the 3z. That's going to be 3e to the 3z minus the z derivative of 2xy plus e to the 3z. So that's going to be minus a 3e to the 3z. So that worked out. That term is 0. For the j component, we'll have the z derivative of y squared, which is 0, minus the x derivative of 3y e to the 3z, which is 0. And finally, for the k component, we will have the x derivative of 2xy plus e to the 3z, which is 2y, minus the y derivative of y squared, which is 2y. So this is going to equal the 0 vector. So yes, this is a conservative vector field. These are the derivatives we took. That's the first x derivative for the y term. That was the second. For the first term, sorry, for the j hat term, we had this derivative, which was 0, minus this derivative, which was 0. And finally, for the k hat term, we have this derivative minus that one. All ended up being 0, so this is a conservative vector field. Now we want to find the potential. So what do we know? We know that the vector field is equal to the gradient of some potential function. So the x component of v has to be y squared, the first component of f. The y component of v is the second component of f, which is 2xy plus e to the 3z, and the z component of v is the third component of f, 3y e to the 3z. Great. So we're going to integrate with respect to x here and get v must be xy squared, plus there could be other stuff involving y and z here. Right? Because if we're taking the derivative of that with respect to x, stuff involving y and z would just go to 0. We'll integrate the second term with respect to y, and we'll get, looks like xy squared plus y e to the 3z plus some function of x and z. And then we integrate the third, this v sub z, integrate that with respect to z, and we will get the integral of e to the 3z is 1/3 e to the 3z, so we get y e to the 3z, and then we could have some combination of x and y still there. So we put everything together, looking at the things that are similar. I've got an xy squared for sure. I've got a y e to the 3z, and that's it. That y e to the 3z is the f of yz in the first one. The xy squared is this h of xy, and this g of xz is just a 0 for this case. So we put everything together. That's our potential function. We can always check by taking the gradient of that and seeing that we get our original vector field f, and we will if we check. So that's it. We can do line integrals now with this, knowing the potential function. But that's the process with 3 variables. It's a very similar process, but I wanted to show you an example with 3 variables.